Welcome to Lecture 1 in the Economics of Disasters. If you're listening to this lecture, then you and your mystery-solving colleagues have reached consensus on the overarching question, are disasters good for the economy? Now, in case you didn't catch my oh-so-subtle hint, let me be very clear. If you have not completed the group problem, you shouldn't be here. Nothing personal, but you need to do the activity before listening to the lecture. So consider yourself kicked out of the lecture hall for now. Please check back on the assignments page, and I'll catch you here later. If you have already wrestled with the clues, you've hopefully come to the conclusion that disasters are not good for the economy, or at least you're aware that economists say they're not. However, you probably still have questions, and we'll try to deal with them. First, despite the economic consensus, the unsettling fact remains that there are seemingly credible and intelligent people who say disasters are good. And there's also those inconvenient examples of people who seem to have benefited. What about them? Our goal in this lecture is to use the tools of economic reasoning to answer those questions. I want to start by identifying a working vocabulary for this unit. As you think about the transfer of this material from you, the adult learner, to you, the teacher crafting lessons for the classroom, add this vocabulary list to your mental checklist. These are the conceptual tools students will need in order to effectively analyze the impact of disasters, either disasters in history or those in tomorrow's news. When we ask whether disasters are good for the economy, it's probably good to know what we mean by the economy and what measurements and standards we're going to use to determine what's good. For our purposes in this unit, the economy is the big picture of a nation's economic activity, that is, its output, which is measured as gross domestic product, or GDP. Looking at GDP before and after disaster gives us a way to capture economic impact. However, an important caveat here is that when we make such comparisons, we have to be careful to talk about real as opposed to nominal GDP. GDP is the total final value of all goods and services produced in a nation in 1 year. Calculation using current prices gives us nominal GDP. But real GDP is adjusted for inflation, which gives us a measure of actual output, not just its monetary equivalent. In the models and examples developed in this unit, unless clearly stated otherwise, comparisons across time or among economies are comparisons of real GDP. Next, the question of what's good for the economy can also be addressed by looking at measures of economic well-being or standard of living. The commonly used measurement is GDP per capita, an average calculated by dividing total output by total population. Again, the caveat is that this is real GDP per capita. It's probably worth noting here that students are often skeptical that such a simple monetary calculation can capture the reality of people's everyday lives. While understandable, their skepticism is misplaced. The widespread use of GDP per capita as a measure of standard of living, not only by economists, but by organizations like the United Nations that are concerned with human well-being, reflects a high correlation between that statistic and such social measures of well-being as, for example, life expectancy, infant mortality, kilocalories per day, average years of education, or even access to clean water. Many of you have taken FTE's online course on Is Capitalism Good for the Poor, and you're familiar with the discussion of poverty measurement in the lesson on what is poverty and who are the poor. For those who are not familiar with the unit, it's available on the website at www.fte.org/capitalism. And a quick read of the first lesson may be helpful if you have additional questions on the validity of using GDP per capita as a measure of economic well-being. Finally, comparisons of economies and economic well-being before and after disasters often incorporate analyses of economic growth. And here again, in our study, we'll adopt the standard definition: changes in real GDP and/or changes in real GDP per capita. While this seems straightforward enough, confusion can occur if we fail to clearly distinguish between level and rate when discussing changes in GDP or GDP per capita. When confronted with statistical measurements of economic change or with analyses that seem to disagree, train yourself to make sure you're dealing with apples to apples and not apples to oranges comparisons. An apples to apples comparison of the level of GDP at 2 points in time is a useful comparison. A comparison of the level of GDP at one time to the rate of growth of GDP at another is an apples to oranges comparison and is very misleading. Economic analysis of disasters starts, as all economic analysis must, with the fundamental condition of scarcity. And the incontrovertible fact is that disasters increase scarcity, and they reduce the output of economies. If we come back to first principles, that resources are necessary for production, then it must clearly be the case that when a disaster destroys resources, total production in the economy must fall. While part of the magic of economic growth is that over time, more output can be produced with fewer inputs, the over time qualifier eliminates this effect in a disaster. Here and now, in this disaster, fewer resources are available and thus less can be produced. Real GDP must fall. It makes sense, however, that the magnitude of the impact on GDP is related to the magnitude of resource destruction. And something that may not be immediately obvious, it's also related to what kinds of resources are the most impacted: land, labor, or capital. The economic model of the production possibility frontier, or PPF, is a helpful tool in sorting out the impact of particular disasters and of answering that pesky question of why the belief persists that disasters can be beneficial. So here's a standard production possibilities graph. Like all models, it's built upon some assumptions. First, the model assumes that all resources are used to produce some mixture of two outputs, which are represented by the two axes of the graph. Usually, these are general categories of outputs. Goods and services is one example, consumer goods and producer goods, or the classic guns and butter, military and non-military goods. These often appear in textbook examples. In our example, the production alternatives are food and non-food items. So our model is looking at a situation in which all the resources in the economy we're studying, all the land, labor, capital, and entrepreneurship, are being used to produce either food or things other than food. The second assumption of the model is that the curve or frontier represents the maximum production possible at this point in time, hence the name production possibilities. Another way to think of this is that a frontier is the farthest edge, so the curve on the graph represents the edge, the most that could possibly be produced with our current technology and all the other resources we have available. Okay, so how do we know what the curve looks like? The points at which the curve intersects the axes are determined by positing that all the resources are used to make only one of the two alternatives. In our case, either all the resources are used to produce food and no non-food items are produced, or all the resources are used to produce non-food items and no food is produced. So we can set up the graph to model the circumstances in different types of economies. For example, here's how we might picture a pre-industrial society living in an area of rich natural resources. Or, how about Japan, with advanced industrial technology but few resources suited to food production? Okay, so back to our generic model. As we said, all points on the frontier are possible, and each point represents a choice of what combination of output alternatives will be produced. The amount of food is measured on the horizontal and the amount of non-food on the vertical axis. Of course, other choices or combinations are possible. Parenthetically, although we don't use it for that in this unit, Note how the PPF model illustrates opportunity cost. Increasing the production of food items means giving up some non-food output. Thus, the points on the curve show the maximum possible output of the two categories of production. But remember that the model assumes all resources are fully employed. Maximum efficiency, no waste. Now, suppose an economy has chosen to emphasize non-food production, but isn't using its resources to full capacity. How would that show up on our model? Right. The dot representing the economy would have to be inside the frontier. The economy is not realizing all the possible benefits of its available resources and technology. Although there are many reasons a nation might not be able to realize its full production possibilities, countries in Africa hampered by repressive government come to mind here as real-world examples. In any case, the model helps to illustrate the advantages, more output, higher standards of living, of trying to move toward the frontier in order to capture the full benefit of your resources. But before we go on to look at the changes in the frontier itself, one last question. What about this? A point beyond the frontier. Given the assumptions of the model, what does that represent? If you said a dream, you've got it. It's not possible to be outside the frontier. Remember the assumptions. The curve represents the edge of what's possible given the current available resources and technology. So, to get to the production combination represented by our X'd out dot, something has to change. Remember our base assumption of using all available resources, including technology, to the best possible use. What if one of those fundamental conditions changes? Well, what happens is that we are facing a different frontier, and in our model, the curve moves. Technological advances, or the discovery of new resources, makes more production possible. The frontier moves out to the right. And finally, we get back to the problem of disasters. What happens when resources or technology are destroyed? Less production is possible. The frontier shrinks as the curve moves in and down to the left. Before we go on with the production possibilities frontier model, I want to take a minute here to review the relationship between resources and output. The concept is productivity, or output per unit of input. Fundamentally, productivity is a function of the available human and physical capital. What this means is that an economy's level of production depends on the mix of skills and abilities of the labor force and the capital, that is, buildings, machinery, tools, and technology that is available to those workers. Our teaching profession probably makes us acutely aware of the importance of developing human capital through education and training. Certainly, we know that workers with machines can produce more, but we may not be consciously aware that physical capital is absolutely essential if we're to realize the potential embodied in human capital. Now, education is good, sure, but it's not the whole story. The amount of physical capital available to the worker is a key determinant of labor productivity, which we measure as output per man-hour or output per person-hour, if you prefer. So what we're asking is, how much physical capital is available to workers, both directly in the form of tools and machines, and indirectly in the form of infrastructure? The importance of infrastructure capital to productivity shouldn't be overlooked. Workers with tools and machines can produce more than workers with none, sure, but it's also the case that infrastructure capital like highways, hydroelectric dams, and communications networks is critically important to worker productivity. Think, for example, of the Soviet Union, where rotting production from the collective farms testified to the lack of effective transportation and communication between farms where the food was produced and cities where it would be consumed. So with that in mind, let's go back to disasters. They destroy resources and thus reduce output, yes, but not always in exactly the same ways. Think of the different resource impacts of, say, a massive earthquake compared to an outbreak of the Ebola virus, for example. In addition to reducing the total amount of available resources, disasters can change the mix of resources. Particularly important for answering our question is the resource mix of human and physical capital, what is known as the capital to labor ratio. This ratio changes in different directions and varying magnitudes depending on the type and size of the natural disaster. As we go back to our PPF model, we can illustrate how changes in the capital to labor ratio affect our perception of whether a disaster was good for the economy. Here's an example. By destroying resources, the disaster has forced the PPF inward. But why did it move further on the services axis than on the goods axis? Well, think about the capital to labor ratio in the production of goods compared to the production of services in our economy. Which is more labor intensive, which is more capital intensive. The impact of the disaster modeled on this graph was greater on the more labor intensive service production than on the more capital intensive goods production. What's more likely to produce that effect? An outbreak of the Ebola virus or an earthquake that ruptures major transportation arteries? So, to generalize, let's look at the PPF models for significant changes in the capital to labor ratio. If the capital to labor ratio falls, meaning that the disaster reduces the capital available to workers, then capital-intensive production will be hit harder than labor-intensive production. To use our examples from above, an earthquake that ruptured major transportation and communication infrastructure with minimal human casualties would have a greater impact on capital-intensive production, shipping, manufacturing, etc., than on labor-intensive services. Thus, on the PPF below, there's a greater shrinkage on the vertical axis. On the other hand, if the capital to labor ratio rises, meaning the labor force is drastically reduced, so there is on average more capital available per worker, labor-intensive production will fall more than capital-intensive production. This is our graph on the right. An Ebola pandemic, for example, would impact labor-intensive subsistence agriculture more than capital-intensive information processing or mechanized assembly line manufacturing. On the PPF, this would appear as a greater shrinkage of the horizontal axis. Got it? All right, let's see. I'm going to go through the natural disasters referenced in this unit, and you decide whether the capital to labor ratio rose or fell. I'll give you the basic facts, but if you haven't already done so, take a few minutes after the lecture to browse through the unit's disasters catalog. It's under the Disasters Home tab on the website. Note especially the great eyewitness descriptions that I won't have time to read here, and the data and research links. You may find both of those very useful with your own students. Okay, so first up is the San Francisco earthquake and fire. An 8.3 magnitude earthquake along the San Andreas Fault on April 18, 1906. Massive citywide fire. April 18th to 22nd, city burned from ruptured gas lines and stoves that were toppled by the quake. Of the approximately 400,000 residents of San Francisco, there were 3,000 casualties. Estimates of total property loss and damage range from $235 to $400 million, which would be equivalent to over $100 billion today. So what do you think? Did the capital to labor ratio rise or fall? Contestants, please lock in your answers. With no intent to trivialize the deaths of 3,000 people, it's clear that the loss of capital was disproportionately greater than the loss of labor. The capital to labor ratio fell. And so it's hard to find any way to think about this as being good for the economy, and it doesn't even appear that way. Next up, The Great Chicago Fire, October 8, 1871. Fire destroyed 3 square miles of the city, including 17,500 buildings valued at over $250 million. It represented a third of the buildings and a half the total property value of the city of Chicago at the time. To give you a sense of the scale of destruction, if we adjust $250 million using relative share of GDP, we get $434 billion in 2006 dollars. About a third of the population of Chicago lost their homes, but no official casualties were reported. Now, on another note, while the culpability of Mrs. O'Leary's cow was never confirmed, she did become a social outcast and had to move away from the city. Okay, so what's your answer? Did the ratio fall or did the ratio rise? In terms of our categorization of disasters, this is the same type as the San Francisco earthquake, in which the capital to labor ratio falls, reducing total GDP and reducing the productivity of a labor force that now has access to less capital. We wouldn't expect to see an increase in per capita GDP in this instance either. What about here? The Spanish influenza of 1918 and 19. Estimates range from 20 to 40 million deaths worldwide. 675,000 deaths in the United States alone, 550,000 of those categorized as excess deaths, or beyond the normal annual mortality. Quoting from a 2003 study, quote, "The influenza epidemic swept the world in 3 waves, the first in the spring of 1918, the second deadly wave in the fall of 1918, and a third wave that further afflicted some regions as early as 1919. The precise origin of the epidemic is unknown, but the first recorded outbreak worldwide occurred in March 1918 among Army recruits at Camp Funston, Kansas. The virus spread quickly across the United States and reached Europe in a matter of weeks, apparently with the arrival of American troop ships. Victims died with excessive accumulation of bloody fluid in their lungs. A distinguishing characteristic of the 1919 epidemic was that it disproportionately killed not children and the elderly, as is usual with influenza, but men and women ages 15 to 44. Numerous eyewitnesses' accounts by doctors and other medical personnel attest that influenza killed the most robust individuals in the population. In my parentheses, read the labor force. For example, the acting Surgeon General of the Army remarked that the influenza epidemic kills the young, vigorous, robust adults, and public health measures taken by local authorities proved completely ineffective at halting the spread of the virus. Now, this is different from Chicago and San Francisco, isn't it? We have, in effect, a worldwide decimation of the labor force, compounded incidentally, but not unimportantly, by the death toll of World War I. But man-made disasters are a topic for another time. So, what happened here? Clearly, the capital to labor ratio rises. Remember what this means, that there is, on average, more capital per person available to the people who survived the epidemic. This is an important clue as to why we can sometimes be fooled into thinking that disasters are good. And we'll come back to that later. Okay, so the last few should be pretty easy for you now. The Asian tsunami of 2004, generated by a 9.1 magnitude earthquake off the coast of Indonesia. The United Nations estimates of 200,000 dead and more than 40,000 missing, but they note that the toll may be understated because of government's inability to provide accurate population data. Relief agencies estimated that 1/3 of the deaths were children, and the U.S. Geological Survey estimated that 1.1 million people were actually displaced. The picture on the slide indicates the scale of physical destruction in a relatively less developed area of the world. So what do you think? Sorry, just a little trick there. Places like Banda Aceh got a double hit. Huge losses of both capital and population. The production possibilities curve collapsed for many of the local economies, with both total and per capita GDP falling. Next up, the Black Plague. Perhaps because of the distance in time, we often don't appreciate the magnitude of the impact of the Black Plague on Europe, the deadliest wave of which ravaged the continent from 1347 to 1350. Approximately 20 million people, or about 1/3 of the total population, succumbed to the plague. The effect of population loss was exacerbated by the breakdown in community and the accompanying tide of fear. Giovanni Boccaccio described Florence in 1348. No doctor's advice, no medicine could overcome or alleviate this disease. Very few recovered. Most died within about 3 days of the appearance of the tumors. The violence of this disease was such that the sick communicated it to the healthy who came near them, just as fire catches anything dry or oily near it. To speak to or go near the sick brought infection and a common death to the living. And moreover, to touch the clothes or anything else the sick had touched or worn gave the disease to the person touching. Such fear and fanciful notions took possession of the living that almost all of them adopted the same cruel policy, which was entirely to avoid the sick and everything belonging to them. One citizen avoided another. Hardly any neighbor troubled with others. Relatives never or hardly visited each other. What is even worse and nearly incredible is that fathers and mothers refused to see and tend their children as if they had not been theirs. People remained in their houses either through poverty or in hopes of safety and fell sick by the thousands. Since they received no care and attention, almost all of them died. Many ended their lives in the streets, both at night and during the day, and many others who died in their houses were known only to be dead because the neighbors smelled their decaying bodies. Dead bodies filled every corner. Most of them were treated in the same manner by the survivors, who were more concerned to get rid of their rotting bodies than moved by charity towards the dead. They carried the bodies out of the houses and laid them at the door, where every morning quantities of the newly dead might be seen. Now, isn't that a delightfully cheery scenario? So what do you think? Right, put it up there with the Spanish flu. The capital to labor ratio rose. Are you starting to see a pattern here? We had lots of writing after the Black Death talking about increasing standards of living, as the people who survived had more capital available to them for production. Okay, last but not least, Hurricane Katrina. There's a long list of Katrina resource material in the unit, but for now we'll just let you depend on memory. Okay, I'm sure you quickly decided that Katrina is similar to the San Francisco and Chicago disasters in the disproportionately greater damage to capital, damage which, unfortunately, the New Orleans economy continues to suffer. We could, of course, continue to add disasters to our catalog. The completion of the Economics of Disasters unit was closely followed by the devastating California fire season, and as we record these lectures, Hurricane Ike has left its mark on the Texas coast and the American Midwest. So it goes without saying that the list will continue to grow, and it's important to point out that you need not feel bound to the historical examples we've used in the lesson. Even at this point, you've already acquired a tool to begin analysis of the next disaster as you consider how it affected the capital to labor ratio. Before we end this lecture, it would be nice to finally answer the questions we started with, wouldn't it? So let's go there. First, are disasters good for the economy? No, unequivocally no, and for good measure, no, 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 no. We live in a world of scarcity, and when that constraint is tightened, when resources are destroyed, regardless of whether those resources are land, labor, capital, or entrepreneurship, our ability to produce goods and services to satisfy people's wants and needs falls. It must. Our conventional measure of the ability to satisfy wants and needs is GDP, gross domestic product, total output, and disasters reduce GDP by reducing our ability to produce. Output falls. With reference to the model we've developed here, the production possibilities frontier must shrink. Case closed. But what about the other question? What tools have we developed here to explain why perfectly intelligent people seem to be fooled? Why might disasters seem to be good for the economy? One answer to that question lies in disaster-caused changes in capital to labor ratios. When capital to labor ratios rise, productivity may increase, if the surviving workers are able to increase output because of their increased access to capital. When the output of these now more productive workers is divided by a smaller population, GDP per capita can rise, even though total GDP may have fallen. Aha! Mystery solved. If we gloss over the implications of reduced population, which we'll look at in the next lecture, the GDP per capita data may lead us to the perception that the disaster left us better off because standards of living for the survivors rise in the aftermath. Here's how it might work. Imagine a medieval village in which the practice of dividing land among heirs has resulted in poor farmers working less land than they were more able to if they could acquire more capital. An epidemic sweeps the village, reducing population by half. Some families are completely wiped out. Their huts stand empty, their land idle, and any horses and plows are unused. While the total production of the village drops dramatically, surviving individuals may fare relatively well as they expand their farming onto the idle land and appropriate the unused livestock and tools. Standards of living after the disaster, measured in GDP per capita of the survivors, rises. Lesson 1 develops this analysis further with case studies of the Black Plague and the Spanish flu that draw on the tools that we've developed here. GDP, GDP per capita, an awareness of the difference between rate and level in comparing GDP before and after disaster, and understanding of the impact of changing capital to labor ratios on productivity. We won't delve into them more in this lecture, but you'll find the discussions in Lesson 1 online. After you complete the first reading assignment for Lesson 1, we'll come back and look more closely at population loss and the hidden costs associated with disaster-produced increases in standard of living. How accurately does GDP per capita data capture the net impact of population decline on an economy?